Hello everyone, welcome back to the next episode on complete reference to CUDA programming. In previous episode, we have seen what are the challenges of increasing the performance of a single core CPU. In this episode, we try to understand how we can improve performance of CPU by increasing the number of computing resources. Right before that, let's talk about a very interesting law in case of computer science and engineering, that is Moore's law. So this law is stated in 1960s by a very famous scientist Moore, and according to him the number of transistors on your processor gets doubled every 12 to 18 months. So that was the law stated by Moore in 60s. Now that law was still valid till, from what I feel, is around 2005 to 10, because we tried to reduce the transistor size and tried to put more and more number of transistors on single core. But as I mentioned in this previous episode, that now transistor size is reached to its physics limit and we are not able to put more and more number of transistors on a single core. So nowadays it is the count of transistor is not getting doubled every 1 or 1.5 year. So that's the reason what I feel that today Moore's law is dead. Again, the people argue or debate about that. They say that Moore's law is still valid. Some say that Moore's law is dead. But from my point of view, Moore's law is already dead because we are not able to increase the number of transistors on a single core. However, some people argue that we can add more number of cores on a single processor, and the same way we can increase the number of transistors on the single processor die. But according to the Moore's law, it was not defined whether it is for it was not defined for multi-core CPU. It was defined only for single core CPU. So that based on that, I can say that Moore's law is dead for single core, right? But some people again say that it's still valid because we are adding more and more number of cores on the same die. So again, it's topic of debate. So let's skip that debate now, and let's say why we are having so limited number of transistors, and if some number of transistors are limited, what is the other solution, right? So maybe if you see the human history, or we are having 100 billion neurons for at least last 35,000 years, and with the same neurons we have learned to do many more things, right? So maybe we can have a completely whole new game to effectively utilize, or new ways to utilize these 100 billion, maybe 10 billion transistors, right? But that is not our context to how to utilize in different way these transistors, but rather than we'll move towards our third scenario that we skipped in our previous episode, that is increasing number of resources to increase the performance. So rather than making a single core CPU core very powerful, why can't we go and add few more cores on the same processor? That means we'll increase the number of computing resources. So if you recall, in the first or second episode, I mentioned three scenarios. First scenario where a worker was having very poor efficiency, then we tried to improve the efficiency of that worker, right? And same context, we have seen a poor efficient computer, and by means of different parameters, how we can improve the performance of these single core CPUs. But we have seen limitation for most of the parameters, and that's the reason we are not able to increase the performance of single core CPU. Now to overcome that, what we can do, we can have a single processor, and on the same processor I can have more number of more number of cores. So first let's understand how a typical computer system architecture looks like. So we'll be having, first of all, on your motherboard will be there, and on your motherboard there will be a processor socket. Now on this processor socket, we can mount a processor here, and on this processor we'll be having multiple cores. So this is the hierarchy. We'll be having motherboard. On motherboard we'll be having a on motherboard we'll be having a processor socket. On processor socket we can fix a processor. Then on a processor we'll be having multiple cores here, and now we can say this particular architecture as multi-core CPU. Similarly, I can also have multi-processor architecture where rather than having only one processor on your motherboard, I'll be having two processors on motherboard, and every processor may be having two cores. So in that case, I'll consider it as a quad core processor. So in this context here, we are having dual core processor on a single processor if we are having two cores, and that's why the name is dual core. Now, for every core, it is having its own register memory. So some dedicated number of registers are there, and that is a smallest memory unit, a memory storage unit in your computer system. Maybe in terms of few bytes, we can store this information on these registers. Now, for every core, we'll be having a dedicated cache memory. So here I'm having L1 cache memory. So L1 cache is again split into two parts, instruction part and data part here, but we are not going to the details of the reason for that. So we'll just simply trying to understand the computer architecture, how cores are organized and how memory layout is maintained on multi-core architecture. So L1 and L2 caches are the nearest to the cores and they are having fastest access time. That means we can access data from L1 cache at faster rate. Then we'll be having L2 cache memory, which is comparatively slower than L1 cache memory. And then we'll be having a common L3 cache memory will be there that will be shared between core 1 and core 2 of this processor. Then we'll be having your main memory, that is typically we call it as a RAM. And then we have finally your hard disk, right? So this is the computer system, typical computer system architecture. Just to give quick recap, we are having motherboard on which processor socket. On processor socket, we have processor. Then on processor, we'll be having multiple cores. In multiple cores, we'll be having dedicated fastest memory, that is register. Then L1 cache, L2 cache, L3 cache, main memory, and hard disk. And they are arranged, you can see, based on the distance, we can say who's having the longer latency. So hard disk is the having longer latency because if you want to access data from hard disk, first of all, it will be brought into main memory, then cache memory, then L2 cache, L1 cache, and register, and then will be fed to the core. So this is about typical computer system architecture. Now we were talking about why to limit ourselves to only limited number of cores, right? Only one core. So we can put more number of cores. And the idea behind putting multiple cores is we can divide the task among multiple cores here. So you heard these terminologies like dual core processor, quad core processor, octa core processor. Even nowadays, you can observe if you go into the system specification in your mobile phones, you'll find out that the information about how many cores are present in your mobile phone. And typically nowadays it is common to have 8 number of cores in your mobile phones as well. So that means nowadays we are increasing number of cores on your processor. Whole idea behind increasing the number of cores is to divide the task among multiple cores so that overall runtime will be reduced. But the question is how to utilize these cores. I can say I'm having 8 number of cores, 60 number of cores, or even 32 number of cores are possible. Nowadays it is common. But how to exploit these cores? To understand this, let's have a simple question here. Suppose I'm going to write a matrix multiplication program using C programming. Uh, Listen this statement very carefully. Suppose matrix multiplication program I'm going to write using C programming language. And now I'll execute that program on 4 different types of CPUs. Assume the rest of the parameters are same for all these processors. Rest of the parameters in the sense clock frequency, pipelining architecture, etc. is going to be the same. Only difference is that they are in different in number. So first processor is single core processor, second processor is dual core processor, third one is quad core, that means four cores are present, and fourth processor is octa core. So here four options are there. You may pause this video and think on which particular processor my sequential C program will execute faster. I hope you got your answer here, and the correct answer to this question is none of this, right? None of this in the sense, if I execute sequential C program on all these processor, it will be executed in same amount of time. The reason is we have more number of cores here, but unfortunately we have written the program that is in sequential C program, and that's the reason it will be executed sequentially, or it will exploit only single core on the processor. The reason is C programming is designed with assumption that the program will get executed on only single core. Now question is, whose responsibility to exploit remaining cores? The answer to this question is the parallel programmers, right? It is the responsibility of parallel programmers to understand the data, to understand the sequence in which the program is getting executed, to understand how data can be decomposed on multiple cores, how it will be executed in parallel, and how results will be gathered as a final result. So that's the responsibility of the parallel programmer. So in short, it's the responsibility of parallel programmer to divide the task among multiple cores, right? Now, there are two common parallel computing architectures are there, shared memory architecture and distributed memory architecture. And out of which we'll be focusing in CUDA programming only the shared memory architecture, because GPUs are based on shared memory architecture. So here we can see the difference between shared memory and distributed memory architectures. On your left, we are having a shared memory architecture where we are having CPUs, four number of CPUs are connected over a network to the memory. Now, let's suppose first CPU wants to send data to, let's say, fourth CPU here. How they will perform the communication? Let's say they want to send a variable value from CPU 1 to CPU 4. It simply happens through this memory. So CPU 1 is going to write some value in the CPU main memory, and from that location CPU 4 will read that value. So this way the communication is going to happen in case of shared memory architecture. In contrast to that, we are on your right, we are having distributed memory architecture. So you can see here, every CPU is having its own memory, and all the CPUs or cores are connected over the network. Now, how communication is happening in this case? By message passing. Now, let's suppose this CPU wants to send any data to this CPU, then it will send a message targeted to this particular CPU, and the message will be transferred over this network. And this way communication is going to happen in case of distributed memory architecture. Out of which, as I mentioned, we'll be focusing only on the shared memory architecture in our CUDA programming series. So this is again little bit zoomed in version of this multi-core processor. Here we are having, whenever we say multi-core processor, means we are talking about CPU which is having more than one core. As I described in previous animation, how the processor is going to organize the number of cores. So we'll be having complete these outer boundaries indicating a processor on which we are having the four number of cores, and every core is having individual memory, that is L1 and L2 cache memory, and then we'll be having a shared memory among all these cores, that is called as L3 cache memory, and over the network we'll be having here off-chip components such as main memory here, right? So here this is called as multi-core processor, and to be specific about that, it is a quad-core processor because it is having four number of cores. So that's it about introduction to this parallel computing and some terms that are very common in case of parallel computing. So in the next episode, we'll try to emphasize on performance metrics in parallel computing. So stay tuned for the next episode.